Hello, everyone. My name is Mariela Sarestoniemi. I'm a postdoc researcher from University of Oulu, Finland, from research units of Medical Imaging, Physics and Technology, and from research unit Center for Wireless Communications. And now I will give you a presentation of our paper, Breast Cancer Detection Feasibility with ultra-wideband flexible antennas on wearable monitoring vest. And this research has been done as cooperation with Professor Jarmo Reponen, Dr. Marko Sonkki, Professor Sami Myllymäki, Professor Karos Komalasarais, Professor Osmo Termonen, and Professor Teemu Myllylä. Here you can see the outline of my presentation. First, introduction, some background and motivation for this work. Then I will explain you the basic idea of breast monitoring vest. And then about the study case, about the antenna model we used in the evaluations and the simulation model. Then the numerical results with power flow evaluations and radio channel evaluations. And then summary and discussion and future work. So first, introduction. As you know, breast cancers are the most common women cancers, which can cause 90,000 deaths in the European Union area every year. Regular population-based screening decreases significantly this mortality. So if these kind of malignant tumors can be found in early phase, it definitely improves the prospect of the cure of the patient. Digital mammography and usually in some cases additional ultrasound examination are the most commonly used screening methods. But these mammography devices are large and expensive, and thus they not can be found in healthcare centers, but only in these kind of larger hospitals. However, only 43% of the invited women participate in these regular screenings. And the reasons for non-participation in this mammography screening has been found to be distance between the woman's home and the hospital where the screening is conducted, but also fear of cancer or negative experiences, and especially the pain during the mammography. However, these kind of aggressive breast cancers may appear and grow fatally rapidly in short time, and thus these kind of frequent regular breast health checks are necessary, especially for women with increased breast cancer risk. In addition to these above-mentioned reasons for this non-participation, also pandemic situations may occasionally limit the possibilities for timely examinations in hospitals. So these are the reasons why it would be important to develop methods for breast cancer detection and with the applications that would be accessible also in smaller healthcare centers and even suitable for home monitoring. Recently, there has arisen interest on developing self-monitoring devices for microwave-based breast cancer detection. So as mentioned, these kind of easily accessible devices could reach better also those women who usually refuse from participation on invited regular screening, for example, due to the distance to the hospital or fear of the pain in mammography. Besides, this self-monitoring vest would enable women to check their breast health more often than every second year in regular checks, which of course facilitates the timely detection of rapidly spreading and growing aggressive cancers. And this is very important for women having higher risk for breast cancer. So aim of our study is to propose using wearable, flexible, small-site antennas on the breast cancer self-monitoring vest. And these antennas would operate at standard site ultra-wideband as well as ISM band 2.45 GHz. Also, our aim is to show with power flow and radio channel characteristic evaluations how even these kind of small cancerous tissues change the signal propagation, and also thus also the radio channel characteristics between different on-body antennas at different frequencies. And our evaluations are conducted using anatomically realistic voxel models to make our results as realistic as possible. And now about this breast monitoring vest, the basic idea. So the monitoring vest is based on detection differences caused by cancerous tissues in the ultraviolet radio channel characteristics between several on-body antennas embedded on the vest. And the basic idea of this functionality of the vest is divided in these following steps. So first, as the vest is turned on, the antenna reflection coefficients are measured and verified with the reference data set to check that the vest is properly set on. If some of the reflection coefficients are out of the reference range, which includes typical moderate variation due to differences in body constitutions, the device advises to adjust the vest properly. And next, the channel parameters are measured between different transmitter and receiver antenna combinations. And the channel data is further transmitted to the terminal device, which then further transfers the data for cloud servers for analysis or image construction. Data analysis is performed using massive reference dataset and using artificial intelligence. This massive reference dataset is required to distract natural variations in the channel responses, for example, variations due to individual breast tissue constitutions from the variations due to the presence of cancerous tissues. Besides, all the user's previous measurement results are gathered in this reference dataset, and they will, of course, be used as a main reference in the measurements. So the simpler versions of this kind of device only produce information whether some abnormalities can be detected from the channel data. So the data analysis can be based on several different algorithms, which can be found from the literature. But the more sophisticated versions, and of course expensive versions of this device could produce image based on measured responses. Yeah, there are some image construction algorithms also found in the literature. So anyway, the results of the analysis are sent to the client immediately. Besides, the results are stored in the client's health register, which is also visible, of course, for the healthcare personnel. And of course, if the device detects abnormalities in the breast tissues, the patient is advised to contact clinicians for further examinations. And now we move to the study case and the antenna model. So the antenna has been designed to operate in the ISM whole ultraviolet from 3 to 10 gigahertz, as well as ISM band 2.45 gigahertz. Which means the requirements of wireless body area network standards 15.6. And this antenna is originally proposed in this reference last autumn. And the antenna has been designed to operate when tightly attached on the skin. And that's the reason. And also due to this flexible material, it is very suitable to be used as a monitoring vest in this kind of applications. So here is the antenna structure and the dimensions of the antenna. So you can see it is quite small size, so 3 centimeters and 2 centimeters. And then about the simulation model. The simulations are carried out using Simulia CSD's Studio Suite and with its anatomical voxel model LoRa. This figure here presents the cross-section of the voxel model's breast area, depicting corresponding tissues and tumor locations, as well as flexible antenna. So skin layer, muscle layer, breast fat, glandular tissue, where usually the breast cancer starts to grow. And then here are the flexible antennas, 1, 2, 3, 4, and tumor location 1 and tumor location 2. And these tumors have diameter 1 centimeter, and these tumor locations are chosen to resemble among the most challenging tumor locations in the glandular tissue area in terms of reachability of microwave signal propagation from these on-body antennas. So for example, this location 1 is in the middle of the breast area in these glandular tissues, the propagation depth is 3.5 centimeters to the closest on-body antenna here. And this location 2 is in the outer corner of the breast area, where we have the limited reachability for several on-body antennas. So here only the on-body antenna 4 is relatively close, 2.5 centimeters. And here in this table, you can find the relative permittivity values for breast tissue or glandular tissue and the cancerous tissue at different ultraviolet frequencies. Additional, here you can find the difference between the relative permittivity of the glandular tissue and the cancerous tissue. So as you can see, the difference between this glandular tissue and cancerous tissue increases with the frequency. And now we move to the power flow evaluations. As you remember, power flow is a time average magnitude of the pointing vector. And this pointing vector represents the directional energy flux, so the energy transfer per unit area per unit time of the electromagnetic field. And the flux of the pointing vector through a certain surface represents the total electromagnetic power flowing through it. So here in our study, the power flow values, which we express in decibels here, have been normalized so that 0 decibels is in the maximum. So it means the value at the on-body antenna. So here we study power flow in the tumor location 2, which is more challenging due to the close presence of only one on-body antenna. In these figures, you can see the arrow-based power flow representations at 7 gigahertz. Here in the presence of tumor, here you can see the tumor, and here the absence of the tumor. And yeah, I showed you already in the previous slide that power flow values are calculated in this certain power, in this certain points in the vicinity of the cancer tissue. And here you can also see these values at different frequencies at 3, 7, and 8 gigahertz in these different points in the presence and absence of the tumor and their difference. So as you can see here, the power flow evaluations show that the cancerous tissue clearly changed the signal propagation in the vicinity of tumor compared to the reference case. And so here, for example, we see much more power flow in this left side of the tumor and also here in the right side of the tumor. And the reason for this is that since the relative permittivity of the cancerous tissue is higher than the glandular tissue, the signal is diffracted as it reaches the cancerous tissue edge. So here you can see. This can be noted both in these power flow representations and also in these values here in the table. So as we see, the higher the frequency, the larger are the differences. And also it depends on the location, how large is the difference. So for example, here in this location E and B, the differences are larger, especially here at higher frequencies. Here even 20 decibels is the difference, here 9 decibels. Whereas in the location A, no differences can be found. So that's the reason why we need to use several on-body antennas to detect propagation differences from several different directions and different areas. So as mentioned, why the differences are larger at higher frequencies, the reason is that, as you remember, the relative permittivity value of the glandular tissue and the cancer tissue, their difference is larger at higher frequencies. Another reason is that the wavelength in the tissues is smaller as the frequency increases. So that's why these kind of small tumors, like here in only 1 centimeter, can be detected more easily at higher frequencies. Of course, the challenge with the higher frequencies is that propagation loss is higher at higher frequencies. So plus also the penetration depth is smaller. So that's why this frequency selection is always trade-off, and we always need to think about what kind of antenna can be used. Does it have to be directional, or can it be this kind of thin, flexible antennas? So it's this kind of trade-off. And then we move to the radio channel evaluations. So we evaluate radio channel characteristics in frequency and time domains for tumor case and reference case in locations 2 and 1. And first, the tumor location 1 and frequency domain channel parameters. Here we plot the S32 channel parameter, so 3 and 2 for this tumor location 1. Here for the whole simulated bandwidth from 2 to 8 gigahertz, and here zoomed version plotted only from 7 to 8 gigahertz, where the differences are more visible. So as you can see here, the differences are definitely more visible at these higher frequencies for the reasons I explained to you earlier, because the difference between the glandular tissue and relative permittivity of the glandular tissue and the cancer tissue are higher at higher frequencies, and also because the wavelength of the tissue is higher, smaller, which increases the resolution at higher frequencies. So here, even 1 centimeter diameter tumor causes changes in the channel responses. Also in this case, where the tumor is deep inside these tissues. So here it was like 3.5 centimeters to the closest antenna distance. And here the difference is something 2 decibels, roughly. Here the maximum is here around 7.4 gigahertz in this case. And then about the time domain results. So these time domain results are obtained by performing inverse fast Fourier transform, IFFT, to this frequency domain channel parameter. In this first case, the IFT is performed for the whole simulated bandwidth from 2 to 8 gigahertz. And here in this figure, the IFT is performed only from 7 to 8 gigahertz. So for this frequency range where the differences are more visible. So here in this case, the difference is also the difference between the tumor and reference case is a little bit less than 2 decibels in this main peak. This figure is quite simple because of the short bandwidth where we have performed the IFT transform. And these results are in line with the power flow analysis, so that the channel attenuation is slightly minor in the presence of tumor than in the reference case. And as you remember, the reason for this was those diffracted signals when the signal propagation achieves the tumor edge. So that increased power flow towards the direction where the other on-body antenna is. So that's why we can see that the channel attenuation is lower, minor in the presence of tumor. And then the frequency domain and time domain channel characteristic evaluations in the tumor location 2. So here the frequency domain results between the on-body antenna 4 and 3, which are the closest antenna for the tumor location, and then the time domain impulse response here. And this time domain response has been obtained by conducting or performing IFFT for the channel parameter S43 for the frequency range 7 to 8 gigahertz. So as noted, that differences between the tumor and reference cases in the channel responses are more visible than in tumor location 1. So here we can see differences even up to 10 decibels, whereas in the tumor location 1, the difference was like 2 decibels. And This is due to the shorter distance between the on-body antenna and the tumor tissue in the tumor location 2 than in the tumor location 1. As you remember, it was 2.5 centimeters in the tumor location 2, the distance between the on-body antenna and tumor. And in the tumor location 1, the distance was 3.5 centimeters. So these are online, again, with the power flow evaluations. So these were the example cases in the channel responses where the changes are largest. And as you remember, I showed you in the first figure, in the practical solutions, we have numerous flexible antennas, which are embedded in the west. So channel analysis is conducted between several on-body antenna links. So finally, summary and discussion. Our paper presented a study on using ultra-wideband flexible antennas in breast cancer self-monitoring tests, which could be used for independent breast health check, for instance, in healthcare centers, or even as home monitoring device. And this waste is based on detection differences in the ultra-wideband radio channel characteristics between several on-body antennas embedded in the west. And realistic radio channel evaluations and power flow analysis conducted using anatomical voxel model so that even small size cancerous tissue, in this case it was diameter was only 1 centimeter, can cause clear differences in the signal propagation and ultra wideband radio channel characteristics between multiple on-body antennas. In the case of small tumors, the differences are largest at higher frequencies. And this was because the smaller wavelength in the tissues enables better resolution at higher frequencies, and also because at higher frequencies, the difference between the relative permittivity of the cancer tissue and breast glandular tissue is larger. So in our studies, we have found that promising frequencies for breast tumor detection would be like 7 to 8 gigahertz. And as mentioned earlier, these presented results were example cases of the channel responses where the changes in the channel responses were largest at the most challenging tumor locations. And the practical solution will analyze channel data from several on-body antennas. And these differences in the radio channel data can be detected with sensitive receivers, and the data could be analyzed in several computers with artificial intelligence-based approaches. And as mentioned, this artificial intelligence is needed to get extensive reference data set to understand which variations in the channel responses are due to the differences in the physical characteristics of the breast, like amount of the fat and glandular tissue, and which are due to the tumors of different size. And this ultra-wideband technique is already well known and standardized technique, which enable low cost, low power, small size, safe and reliable devices. And this kind of monitoring waste could be made affordable and easily accessible even for small healthcare centers or even home monitoring use. And as future work, we will do more extensive simulations with different tumor size and different tumor locations using several voxel models having different size and body constitutions. Additionally, different antennas and antenna types will be tested, for example, directional antennas as well, to verify the impact of the antenna properties on the channel response differences. Currently, we are also preparing human tissue mimicking phantoms for breast area and conduct measurements with several antenna prototypes for verification of these simulation results. Thank you very much for your attention. If you have some questions, I would be happy to answer here, or then you can send me email to this direction. Thank you.